Going upstairs and logging on and see if you can hear me. Thanks.
Obviously, it's quite nice.
Yeah.
That's why you put it on hold, I think.
Yeah, it's just okay. But play a trial first and adding one.
Yeah, we do. I've just made the typesetting a bit more. There's been quite a number of sub figures now, but
Yes.
but yeah, the grip frames it looks like that. It's a 1/x plot.
Yeah.
That's
Do you have a feeling for Sean Anderson just to he didn't really strive that.
no, yeah. It's in the grip aspect, so the overall errors will go close to the median actually.
So I need to.
Than any other thing.
Yeah.
There's no reason for it to do that.
Settings.
And you put the covariance rate or correlation matrices assuming two examples. Yeah, but maybe you could do them under the message now. You know, just do them simulations too.
That should be relation. It's not content. You want to see that there? What one?
Yeah,
for the result on the relationship. That should be very easy.
You please different sample sizes so that you get the variances are different. You can see the correlation.
There, Marie.
If the
That's there.
correlation is independent sample
It's
size.
content, focus on content.
Variance
Thank
is
you. I
not.
was looking at
Yeah, I
three
think you
dots.
have to do some kind of setup thing, didn't it?
Correlation could turn their speak result that could.
Can you hear me, Lucy?
I mean, that's
She can't
dream scenario.
Is she on?
Yeah, if the
Yeah.
correlation is independent.
That's says there on there, does it?
No, it shows her on here.
It's actually something that's just pushed.
She can't hear me.
And put it in your archive. Yes, it's been like an archive.
Yeah, most very complicated, but there was some more details.
You only need to be fine, right? It's really
For example,
Green.
Yeah. I mean, obviously, a package doesn't have to be complete.
1 minute, yeah.
You said it's
So again, all the ones.
you can go into submission. To see that. What's out there and it's going to be used in the front.
We need to remove it back. It's not like.
I know, it's really dangerous. I don't know how many times I've tripped over it. Hello, can you hear me?
Yes.
Brilliant. Can you see the screen?
Yes.
You can see the screen. Okay, thank you. It's a summary at the beginning.
Yeah, it's on this, that doesn't know as substantive things and these are the right victims of the violence. And it just means it's going to end less to be maybe not quite the same way but also it's about strength.
I know you've emailed me back, but I haven't read it. It's been a bit crazy today, but I will get back to it. It's just come and find if it's a do your thing, you just come and find me. It's a bit crazy at the moment.
I can do that. I didn't want to be
Yeah.
so that would
No, it's fine.
Yeah.
thank
Should be a little bit quieter this afternoon.
not a problem. I think we
It's a summary. Thank you. Okay. So we just need, yeah, thanks Lucy, that's fine,
No
thank you.
worries.
You can leave, thank you.
Which is used in trials in phase 2 studies. And it's about never be to have those responses. And I feel that maybe similar sort of might have been used on the basis of model averaging. And it might be.
Just so you leave.
Yeah, no.
I told you right.
Yeah,
Yeah, it's all right.
Tom, I didn't to say
I got a first draft of my thesis, so it's like a bit of a weight off. Yes.
Oh, yes, right. So sorry.
Yeah, yeah.
I'm going to ask a terrible question. What year do you cross the corner?
Fine. So, third year. Because we've come out from
They're the ones that
clinical trainees that have to come out, and then that's why the end bosses we get, so have to go back in and then.
Okay.
Yeah.
Otherwise, it's a terrible thing.
I know.
But that would be good.
He works again as the IU.
Well, I don't know about you, but I thought it was all good to begin with, and then you get into the weeds of it, like, oh, no, like, why did they do it like that? It's going on.
Yeah, it looks above you.
If you walk in and you don't feel that should be something.
Yeah.
Yeah.
Sure.
Budget.
I mean, everyone's building different.
Yeah, it's too bad.
It's really fun.
Yeah.
You're writing
And
Yeah. Imagine you go for your phone.
I was thinking
So they give you all the back.
People slide down.
What we were doing, and I made a lot of things that consistent in copy that for the right.
Oh,
I didn't buy so much, so that's why better take it. Yeah, let me do it. Do I have? Yeah. How do I move the flag? Okay. Where am I? Ah, there we go.
People can see you. It is, it's I know, she doesn't understand. Don't worry about it.
I need to find the things and I can use the point I need to.
That's what you work.
Okay.
I already played with I did not destroy it.
He won today.
But I can change it. So it's.
Stand in front of the, so you can see you.
Right for the
I think they need to see you on this pad.
There you go. Hi, people here and people online. It's a pleasure to introduce Fernando Hartwig, who I think many of you know, who's with us for a couple of weeks. He has a part-time position here and largely in office in Gazette. But Fernando's going to talk about MRAGA.
Thanks. Thanks, everyone. It's a pleasure to be back in Bristol. I was counting when I was back on Saturday, and it's the 10th time I visit Bristol. So, and it's always fun. And the last couple of times I've been here, it was during the winter, so it's nice to be here. This time of the year, the weather is much nicer. And today I want to talk about some aspects of hemorrhagic regression. This is the outline of my presentation. Hopefully I'm going to be able to cover everything. And this can be interpreted as a follow-up of a seminar presented here, I think last year, by Frank Ludwig, who is here and is also involved in the work I'm presenting today. As you can see, I enjoyed his seminar. And you can also see I subscribed to the YouTube channel. So it's proof that I'm engaged. So as the starting point of the presentation, I want to discuss briefly a model or the data generating model I'm going to be using throughout the presentation. So when we do Mendelian randomization, our interest is in estimating the causal effect of some exposure X on some outcome Y, and I'm denoting this effect by beta. And we try to do that using one or more candidate genetic instruments. So we have, a bunch of genetic variants, and we hope that they are valid instrumental variables. Of course, we know that they might not be, so that's why we try to use methodologies such as hemorrhagic regression. And the model I'm assuming for the effect of one of my genetic variants, which I'm denoting here by G sub J, is expressed in the slide. I need to move here as big gamma. So big gamma is the total effect of the genetic variant on the outcome. So if your outcome is a continuous variable, for example, then big gamma is typically going to be like average changes in the outcome per copy of your effect allele. If it's a binary outcome, then big gamma is often going to be log odds ratio per allele or something like that. And I'm assuming that the big gamma can be expressed as follows. Alpha plus little gamma times beta. Alpha is the direct effect of the genetic variant on the outcome. By direct, I mean that's not fully mediated by the exposure. And little gamma is just the total effect of the genetic variant on the exposure. And beta is the causal effect of the exposure and the outcome. And you can see there's no sub J for beta, which means I'm assuming that if had all genetic variants being valid IVs, that they would all identify the same causal parameter. And of course, this data generating model for the total effect of my genetic variants on my outcome requires, a lot of linearity assumptions that I am, that I am authorizing myself to make those assumptions because they're typically made in the literature. So I'm just operating on under typical models. I'm not arguing that those models are plausible or implausible. That's not my focus today. And for many linear randomization methods, including hemorrhagic regression, we need the red and the blue here to be uncorrelated, right? We need the direct effects to be uncorrelated with the effects of your genetic instruments on your exposure. But that might not be true. So one of the mechanisms that could violate this assumption, which is called the inside assumption, is illustrated in this diagram. So in this diagram, in red, we have the pathways contributing to the direct effect. And here you can see that one of the pathways is the direct effect from G sub J to Y. And the other pathway is this pathway here, G sub J into U into Y. And we also have the pathways contributing to the total effect of the genetic variants on the exposure, the direct effect delta sub J, and the path G, U, X. And notice both of them have a common component from G to U, and this could cause them to be correlated. So I'm not saying this is the only mechanism that could cause the alphas and the little gammas to be correlated. I'm just illustrating it to make the point that this is not a free assumption. That this is something that could be violated in practice. And what I want to discuss now is that the inside assumption depends on our decisions with respect to which alleles are the effect allele and which alleles are the other allele. For now, I'm just repeating what Frank said in his presentation last year. So here we have a very simple example where we have 4 single nucleotide polymorphisms labeled 1 to 4. For each one of them, I'm showing you different coding schemes. So one coding scheme and coding scheme 2. And I'm showing the variants chosen as the effect allele and the other allele for each one of those SNPs. Here's just made up data. So for coding scheme 1, we have the estimates of the total effect of your genetic variant on your exposure. Some are negative, some are positive. And the direct effects of genetic variants on the outcome. These numbers here, you wouldn't typically know in practice. I'm just showing them for the sake of illustration. And if you take the correlation between the little gammas and the alphas here, it's going to be something very, very close to 0. You can like type in on your computer and do the correlation. It's going to see that that's very close to 0 unless I made a mistake when I was generating this example. But if we do the same thing using a different coding scheme, things change. So here under coding scheme 2, I'm flipping the effect and other alleles for SNPs 1 and 2. So for coding scheme 1, the effect allele was A, and now for coding scheme 2 is G, and the same for SNP 2. And when you do the correlation, you get quite a substantial correlation between the little gammas and the alphas, showing that, illustrating this more general point that the inside assumption depends on your decision on how to code the effect on which one's going to be the effect allele, which one's going to be the other allele. And the coding scheme 2 is very special. It's the all positive coding scheme, which is the coding scheme such that we choose the effect allele in order for effects of genetic variants on the exposure to be positive, to be all positive. So that's hence the name all positive. Okay. So why does this matter? Well, it matters because to answer the question, does inside hold, we should respond with a question. It depends under what coding scheme. And this could be a problem because the coding scheme is typically arbitrary. Typically an arbitrary choice that we make that often has little to no substantive justification for it. And if we have an arbitrary component built into the assumption we need for the validity of a given estimator, it becomes difficult to justify why we would believe or not believe in the assumption that we require. So for example, in the case of MRI regression, it doesn't rely on inside, but it relies on a specific version of inside, which is the inside under all positive coding. And again, can we ever hope to provide biological justification for the plausibility of this version of any other version of the inside assumption, given that it has an arbitrary component built into it? And a possible solution to this problem is to try to find an alternative identification condition that does not depend on allele coding. And that's what Frank Dudbridge and Jack Balding and others did by proposing the MR-GRIP strategy, which essentially takes the data generating model for the total effect of the genetic variants on the exposure and multiplies both sides by little gamma. So now we have a model not for big gamma, but for the product of the gammas, for the product of big gamma and little gamma. And the reason why this is useful is because now the parameters that interest us are the product of alpha little gamma and big gamma and little gamma squared. Little gamma squared is clearly coding invariant because we are squaring things, so it's always going to be non-negative. And this product here is always, it's again coding invariant, because when I flip the effect another allele, I flip the sign of little gamma, but I also flip the sign of alpha. So the sign of this product won't change between different coding schemes decisions. And this is illustrated here with our toy example. It's the same example was before. Under coding scheme 1, we have, little gamma square all positive, and the product of the alpha and little gamma, some negative, some positive. And when we go to the second coding scheme, which had some differences in the previous example, when we look at little gamma squared and the product of alpha and little gamma, we see the same values between the two coding schemes. I'm not saying that this toy example proves the coding invariance property. I'm just illustrating the coding invariance property with this example. But now we are going to rely on a different identification assumption. The identification assumption that has been called the Weiss assumption, which postulates that the product of alpha and little gamma is uncorrelated with little gamma squared. And why do I need this assumption? Because I'm going to be regressing the product of the gammas on little gamma squared. And I want to get a consistent estimate for the beta. So I need whatever is in here to be independent on whatever is in here. So it's a different identification assumption compared to Marega regression. At this point, I'm not going to discuss whether or not this assumption is plausible, implausible. I'm just saying that this is the assumption you would need to get a consistent estimate for your beta using MRGRIP, given the data generating model we are assuming during the presentation. And the point here is that since the two components of the Weiss assumption, the product of alpha and little gamma squared are coding invariant, then Weiss is coding invariant. So now we have an identification assumption that is coding invariant. So at least with respect to coding dependency, it seems like we made a step forward, right? There could be some other costs associated with it, but I don't want to discuss this today because I want to focus on the coding dependency issue. Is that clear? Okay. So the question now is, okay, should we move past MRG regression and forget about it, since now we have a identification assumption that is not coding dependent? And I don't think so. And this is now where I'm presenting things that were not included in Frank's presentation. Up to this point, I'm just copying what Frank presented last time. When we multiply both sides by little gamma, we're multiplying both sides by the absolute value of little gamma times the sign of little gamma, right? And the reason why the MRGRIP model is coding invariant is because we're multiplying not by little gamma, but by the sign of little gamma. This is what achieving coding invariance. And again, this is illustrated in our now familiar toy example, where we had our coding scheme 1 or coding scheme 2 and when you see that when we multiply little gamma by the sign of little gamma and alpha by the sign of little gamma, then we have the same numbers under both coding schemes, illustrating, again, just illustrating that the reason why we are achieving coding invariance is because we're multiplying both sides by the sign of little gamma, all right? So one way to achieve coding invariance is, instead of multiplying by the absolute value of little gamma times the sign of little gamma, just multiply by the sign of little gamma. That would be another way to achieve coding invariance, right? But doing that is equivalent to the all positive coding scheme. So the argument I'm making here, and I'm happy to be challenged, is that if I accept the coding invariance property of MR grip, then it seems to me I have to accept the coding invariance property of the typical implementation of MR regression because they are coding invariant for the same reason. They are coding invariant because I'm multiplying both signs by the sign of little gamma. I'm not saying the two methods are equivalent. I'm saying that they achieve coding invariance for the same reason. And that leads us to a different way of looking at the typical MR regression model under a positive coding scheme. Instead of interpreting it as, I have my estimates and I flipped some alleles so that I arrive at the all positive coding scheme, we can interpret it in a different way. We can interpret it as a model that is coding invariant, doing kind of like what the MR grip model does, but instead of multiplying both sides by little gamma, multiplying both sides by the sign of little gamma. And again, that is equivalent mathematically to the all positive coding scheme. But the point that now we are starting with a model that is coding invariant. And this leads us to a grippy version of Insight. That is a version of Insight that is coding invariant, which is that the covariance between alpha times the sign of little gamma and the absolute value of little gamma is 0. Again, I want to emphasize this. This is equivalent to the all positive coding version of MR. But now I'm just thinking about it from a different perspective. I'm thinking about it starting from a model that is coding invariant. And it is coding invariant for the same reason that the MR grip model is coding invariant. So it seems to me that if we're not happy with achieving coding invariance in this way, then we should also not be happy with achieving coding invariance by multiplying by little gamma. But to me, this all boils down to this question. Can we interpret those parameters in any intuitive way? And I'm saying this because if we can't, then it becomes very, very, very difficult to use prior knowledge to try to assess the plausibility of this assumption or device assumption or any other assumption. Otherwise, we're just like achieving a technical, property, which is coding invariance, but it's not really helping us towards, having better capacity to interpret the assumptions we're making. And I think, yeah.
Interpreting the assumptions or interpreting the result?
No. What I mean is that how can we think about this, if this is likely to be true or not, so that we can trust the result, so that you can trust the result?
Yeah.
Does that make?
Yes, yeah, but to me, some of the manipulations you make also affect the interpretation of the result. From something like, an increase in this unit of BMI causes this, potentially causes.
Yeah, but if let's say, we are happy with this data generating model, and we are happy with this assumption for now.
Yeah.
All right. If that assumption is true, and you regress this, which is observable, on this, which is observable, then you're going to have a consistent estimate for beta, which is the effect of your exposure on your outcome. So from that perspective, it wouldn't change the interpretation of the result, assuming the assumptions are satisfied.
Yes.
All right.
Thanks. Yeah.
And I think, and I want to emphasize the thing here, we can interpret the coding invariant conceptualization of the MR regression model in a way that is, I don't want to say intuitive, but in some way nice, right? And the way I think we can do it is go back to our coding dependent model for the total effect of the genetic variant on the outcome and express the ratio estimand using this model. So the ratio estimand is just the right-hand side divided by little gamma, which equals alpha divided by little gamma plus beta. And that's the bias parameter of the ratio estimand, which you can express in this way. Switch little gamma by the absolute value of little gamma and put the sign of little gamma in the numerator. Those things are equivalent. Now, the parameters of the coding-invariant conceptualization of the MRI regression model show up directly in the ratio estimate. The direct effect of the coding-invariant conceptualization of the MRI regression model is just the numerator of the bias parameter of the ratio estimate. And the thing that's multiplying your beta in your coding-invariant conceptualization is just the denominator of your of the bias parameter of the ratio estimate. And indeed, if you look at it, you're going to see that the ratio estimate is biased downwards if this direct effect parameter here is negative, because it's the numerator, and this is always positive. I'm assuming this cannot be zero because of the relevance assumption. And the ratio estimate is going to be biased upwards if the sign of this direct effect parameter conceptualized in this way is positive. So in other words, the direct effect parameter of the coding-invariant conceptualization of the MRI regression model is closely related to the bias of your ratio estimates, is actually in the same direction of the bias of your ratio estimates. So I think this is a nice interpretation of this model, because it links it directly to ratio-based MR methods like IVW, median, etc. So going back to this conceptualization of the inside assumption, we're going to have that if the covariance is positive, that just means that stronger instruments have on average more upwardly biasing direct effects. If the covariance is negative, it means that stronger instruments have on average more downwardly biasing direct effects. And if there is no covariance, then direct effects and instrument strength frequently are related, at least with respect to covariance, right? So my point here is that we can interpret the typical implementation of the MR regression model by conceptualizing it as a coding-invariant model. And in this coding-invariant model, we can interpret in what is, in my opinion, a nice way, by relating the parameters of this model to the corresponding ratio estimates. So moving towards the end of my presentation, this is something I want to present quickly, because it's we are still working on it. And for now, I'm going to assume the all positive coding, because I presented all the arguments that I wanted to present to support its interpretation as a coding invariant model that can be biologically interpreted. The key question still remains: how plausible is this assumption? That's the key question, right? And when we were discussing, me, George, Jack, and Frank, we came up with this notion that any substantive justification for the plausibility of this assumption should be about independent or distinct biological pathways underlying the effect of genetic variant on the exposure and the direct effects of genetic variants on the outcome. But if that's the case, if you have distinct biological pathways underlying the little gammas and the alphas, then you would expect them to be independent. You wouldn't expect them to be merely uncorrelated. So from this perspective, inside can be interpreted as a de facto independent assumption, even though independence is stronger than we need. And this is because any biological justification for this assumption will typically support the assumption that they are independent, not merely uncorrelated. And I'm going to refer to this for a terminological distinction for this independence condition as a strong insight, as opposed to like regular insight, which is just about covariance. Is that clear, guys? Strong insight is obviously stronger than not strong insight. And that's useful because this offers more opportunity for falsification. When you're making a stronger assumption, you have more opportunities to falsify it. For example, if strong insight holds, then we would expect the conditional variance of big gammas, conditional little gammas to be constant. In other words, we'd expect big gammas to be homoscedastic with respect to little gammas. Notice that here this involves only observable quantities. So this is empirically verifiable. But before illustrating how you can do it, I want to emphasize that strong insight is stronger than insight. So if I reject the strong insight, that does not mean that regular insight is invalid. So why are you proposing this, Fernando? And again, it's about plausibility. If we have evidence that the little gammas and you have some evidence that little gammas and the alphas are dependent in some way, then we have evidence that the biological mechanisms underlying these effects are not independent. And if the biological mechanism underlying these effects are not independent, that should cause us at least some concern about the key assumption of lack of covariance. That's the rationale for this. As an empirical example, George said he likes empirical examples, so I needed to include one. I'm looking at, as an exposure, large particle high density lipoprotein cholesterol. And here in the x-axis, the little gammas are expressed as purely standard deviation changes in this exposure. And in the vertical axis, I have a purely log-odds ratio of age-related macular degeneration. I know nothing about those things. This is just an empirical. This is just for illustration. And I have 25 candidate genetic instruments. And just by looking at the scatter plot, you don't need any statistics here. We can clearly see there is an outlier here, which I marked in red. I remember when I said that we had an outlier in the data, George asked me which method I used to determine it, and I said eyeballing. And this example is very convenient for my application, but we can clearly see just visually that this is causing heteroscedasticity in the scatter plot. And if we do like a leave one out procedure, removing this eliminates all statistical evidence of heteroscedasticity, but removing any other doesn't. So what I did, I just applied different MR estimators to this data before removing this outlier and after removing this outlier. First, before removing the outlier, we have strong statistical indication of heteroscedasticity, as indicated by small p-values in a heteroscedasticity test, and also by quite a big value describing the correlation between absolute residuals from the MR regression model and the SNP exposure effects. And when I remove that outlier, any statistical evidence for heteroscedasticity vanishes. And another way to see that is like if you cover up, and you just see that. And before removing the outlier, the MR estimates are kind of all over the place. Some virtually zero, then indicating some positive effect, and here the confidence intervals largely overlap with the null, but the point estimate's kind of in the negative direction. And when we remove the outlier, we have everything kind of like in the same direction. Of course, this consistency doesn't prove anything. It's just an example to illustrate the procedure I'm describing. So to sort of try to wrap up the presentation, we discussed that the inside assumption depends on the often arbitrary choice of coding scheme, and I agree with that. And MR-grep does offer a solution to it, which is multiply both sides by little gamma. And this model, which is now a model for the product of the gammas, is coding invariant. But we can also achieve coding invariance by multiplying just by the sign of little gamma. And this happens to be equivalent to the all-positive scheme that is typically used in MR regression. And this is useful because this allows us to conceptualize the MR regression model in a way that is coding invariant, and the parameters of this conceptualization can be directly related to ratio methods, which I think aids in their interpretation. Then I also briefly mentioned that heteroscedasticity tests can be used to assess the plausibility of inside assumption under some coding scheme, under the coding scheme you are using. Again, not rejecting homoscedasticity, of course, does not imply inside holds, because we can have, all sorts of different reasons for not detecting something that exists. But more importantly, strictly speaking, this is not a falsification test, because strong inside is stronger than inside. But this again is about plausibility. If we have some evidence that the little gammas and the alphas are dependent, then this ought to reduce our confidence that they are related in precisely the way we need for our estimator to work, especially when we are justifying our assumptions on qualitative knowledge that not always going to be sufficient for us to make assumptions about some moments of a joint distribution, but not others. If you've ever been to one of my presentations, you know what's happening now. Pictures of my family. Those are from the last time I was here. My daughter was still, waiting to be born, and I decided to innovate by showing a video of my children playing. My daughter is gonna turn 1 tomorrow. And my son David is 4 now, and they are now playing. And a lot of thanks to my beautiful wife Jessica, who is very, very supportive, and I do not take that for granted. Sorry, I do not take that for granted at all. And the 3 children that we lost during pregnancy, but will be forever with us in our house. I'll be happy to take any questions. Thank you.
You have to have a video of you playing with him. Questions, Jack?
Thanks, Fernando. Maybe you could just go back to the scatter plot you showed, just because I just wanted to make a couple of comments. Yeah. I mean, this plot is under the all positive code. Isn't it? And I mean, when we were originally developing the method, this coding just provided a way of visualizing the data that just had so many attractive properties, because if we don't do that, what we're looking at is a quadrant of data points that could be, and the advantage of this coding is that I can draw a line from every data point to the origin, and that's the ratio estimate for each variant. And then I can interpret the IVW estimate as a weighted average of all of those slopes. And I can also interpret the distance from each data point as a residual from that line. And then I can add an intercept to the regression and you get MR. For me, it was it gave you it allowed you to plot the data in a way that just had a lot of sort of attractive properties. But then it gave me sleepless nights for many years afterwards because I wasn't sure whether it was arbitrary or not. So yeah, your work is really interesting. Another nice bit of work to add to the debate. So well done.
Thanks.
So just following on from that, would you say that, rather than doing the squared and the other things, we can do the odd positive if we see something like that and take one out where it's only one, but there'll be times when you've got a lot more difference and it's a good starting point. Is that a correct approach?
I think it's a good starting point. And the other important thing is that it's the intercept that's the problem, isn't it? It doesn't matter. Any other method that doesn't estimate an intercept that is some sort of weighted average of the ratio estimates. It's the coding is irrelevant.
Yeah.
And for those methods, this is still the nicest way, I think, to plot the data. And I think sometimes plots are just there to visualize data, but sometimes they can be an analysis tool as well. And this way of visualizing the data gives you both, I think, the easiest. And nice package.
Kind of intercept issue, to me, always felt like the inside assumption applied also to the straightforward IVW.
Yes, yeah, and it's just you need the play trip to have a zero mean as well. Yeah, exactly. So yeah, I don't know if you could say something about how the standard approach relies on inside as well. This sort of stuff.
Yeah, I mean, the standard approach could work if like strong inside, in my sense here, is violated, as long as we still have the balanced pleiotropy. But I think you need the covariance zero.
Yeah.
But I haven't
But now you
thought
have
too
a
much about
less
it.
plausible assumption, though. But you're saying you now have a less plausible assumption.
But no, my point here, I didn't try to make many judgments on like whether these assumptions are plausible or not. My point here is that if I have biological reasons to believe that this is true, then it seems to me that those same reasons would lead me to believe that this is true. And in that, if that's the case, then we can empirically verify the plausibility of that assumption, because that's much stronger, like statistically much stronger. I find it very difficult to biologically, based on independence of biological mechanisms, to justify this without justifying that. Of course, we can throw in some parametric assumptions, some distributional assumptions, and make distinctions between them, but I'm talking about qualitative prior knowledge. In that realm, I find it difficult to justify this without justifying that. And that's what's giving us the leverage to assess the plausibility of the assumption. They can still be utterly implausible. I'm not defending their plausibility. I'm trying to think about a way to assess the plausibility of the assumptions we need without imposing too many things that I wouldn't need otherwise to impose. Yeah.
Thanks, Fernando. It's just beautiful talk as always. And I think that's a good place to lead on to the question that I have, which is, I've spent a lot of time trying to simulate data generated models and in the different scenarios, and in order to create a scenario where you've got a non-zero intercept, the best way to simulate that is to simulate a non-zero intercept. Meaning there are very few what you call intuitive biological models where you go and simulate that, and now you've got a non-zero intercept. It's mostly going to generate something that looks more like, a random effects model, or it's mostly going to look like something that looks like a violation of inside.
Yeah.
And so, in some ways, it feels like it was absolutely. I remember how monumentally
important it was when MREG came out, or came about. It was like a new mode of thinking. But I think like now, if you don't have like a good way to generate to motivate that alpha is going to be non-zero, it's difficult to make a case that this is actually worth solving.
Yeah, no, I see your point. I think one of the things we need to realize that is when you simulated your non-zero intercept, you were probably operating under some coding scheme.
Exactly.
Because you already have your 0, 1, and 2,
Yeah.
right? And when you simulate, now let's think in the flip side. Let's think you simulated a non-zero. You simulate a 0 intercept. If you simulated a 0 intercept under a coding scheme that's not going to be your coding scheme of choice, when you flip things to arrive at your coding scheme of choice, you could induce a non-zero intercept there.
Okay.
So
I have to think about that. But
yeah.
I didn't appreciate it. But that's
So yeah, so that's to me that's the thing to think about. If you believe that under some coding scheme there is a 0 intercept, which is what you want, right? Is that the coding scheme of your choice?
So yeah, if you could to take it offline, I mean, like if you could show me an example where you simulate a 0 intercept, like and then you sort of induce a non-zero intercept.
So the example I have here is not for a non-zero intercept. It's for zero and non-zero correlation between the effects on the exposure and direct effects on the outcome. And because I'm thinking about whether or not inside is valid.
I agree with that. That's totally fine. I'm just thinking about the intercept.
Yeah, that's my response to that was that nature doesn't actually follow any model. So the model with an intercept might fit the data that nature has produced a bit better than the model without. Yeah, that's kind of how I negotiate that one. I mean, I totally take your point. Simulating an exact model that produces that structure might be very difficult, but that model might just fit the data that we're presented with, better than the IBW model.
Okay, I think you're right. Like that, it's an option there to try to fit. And in some ways, like there's a sweet spot, isn't there? Because under the model where you have to put an intercept in, then basically what you're basically saying is that the only other way in which, if you have a million variants, it isn't going to happen by chance. If you have 3 variants, there's a stochastic possibility that you generate non-zeros that can be useful. And
yeah. So this is Ching Wan's argument actually for RAPS, isn't it? His model. So if you have enough SNPs, it's just implausible that there'd be a non-zero intercept. And actually, even if you have 3 SNPs and we assume they come from a random effects distribution, then we should also assume 0. And, I mean, it's a fair enough point. But when you fit the model to data, you sometimes find that the intercept adds information that wasn't there. If I have time to make another Fernando, so the heteroscedasticity test, that is also coding dependent, isn't it?
Yeah. So my point here, so I have 2 separate parts of the presentation. Up to point 3, I was trying to argue that if we are happy with the coding invariance property of MR grip, then I believe we have to be happy with the coding invariance property of the typical implementation of the MR regression model, because they achieve coding invariance through the same means, which is multiplying by the sign of little gamma. And from this point out onwards, I'm using the all positive coding scheme because I presented all arguments that I could for it being a model that can be interpreted, because we can relate it to the ratio estimates. But you could do this to any coding scheme of choice.
And what I'm thinking of is perhaps that test fails under all positive coding, but it doesn't fail under some other coding under which we have not rejected the strong inside assumption. So
Yeah, then I mean, then you can start to, you know, think about ways to move forward.
yeah,
Like perhaps we can falsify coding schemes,
Yeah.
or do something like that, or we can try to develop an estimator, and this is just going to motivate you guys to invite me back for a presentation in the future. We are now working on something that relies on this assumption, which is different than the other two. This is coding invariant because everything is squared. And this is true if we have at least one coding scheme where the little gammas and alphas are independent. If you have at least one coding scheme where that's true, then this is true. So instead of like running over all different coding schemes, we can just try to estimate things based on this kind of identification assumption, which is something we are currently trying to develop.
I think that's something that Ben Neal said in an offhand way. Yes, something like that.
Oh yeah, no.
Quite familiar with it. But
Just one question about this stronger assumption about independent. So I touched on that briefly. So can you come up with any mechanism that gives you independence under the all positive encoding, but does not give you independence under any other encoding? I can't see that because any other encoding is a sine times gamma j or sine times alpha j.
Yeah, so I think that's a very sorry.
So-
Can you finish your question?
Yeah, my point is then if you assume independence, the encoding doesn't matter anymore.
I don't want to say I disagree, but I don't want to say I agree.
Okay.
I don't think that's true.
It's a question, I don't know, but to me, if you multiply something by a constant, something that's already in.
But the thing is that I'm not multiplying everything by the same number, because, for example, let's go to the toy example. Here you can clearly see that, for example, when I multiply things by sine of little gamma for variants 1 and 2, I'm multiplying by -1.
Yeah.
Here I'm multiplying by +1.
Yeah.
So it's not the same for all variants.
Okay, so then you need to come up with a mechanism where it's funny because it would be nice to see a data generating mechanism where you have that, because it means to be that the sign you multiply with is somehow associated with the sign you multiply the alpha with or something.
It is.
There needs to be some sign dependence, is what I'm saying.
It is, because the sign of little gamma is related to the sign of alpha in the following way. When I flip the generic variant, I'm going to flip all the sign of all parameters associated with it.
Yeah. Yeah, I just want, because when I talk about think about independent mechanism, it's not even necessarily statistical independence. It's that they operate through completely different mechanism of actions, like in a sufficient cause model or something.
Yeah, that's what I mean.
Yeah. And this is not the same as the independent symbol somehow. This is like a stronger assumption.
Yeah, but my point is that what I'm saying here is any substantive certification for the inside assumptions should be about distinct biological preference.
I agree.
That's my point.
That's where I want to.
That's my point.
To the.
So-
But so, let me just finish responding. So if that's true, if you have a completely different structure underlying these two effects, then I would expect this.
I think I agree with that too. And then I want to go further and ask, can you come up with an example where then you get a coding dependent covariance? Because in other words, if those assumptions imply that the first thing, the all positive or coding one,
I see what you mean.
yeah, then you could just go back and use Jack's all method.
Yeah, I see what you mean. I don't want to make any assertive response now because I haven't really thought too deeply about what you're saying. But I see your point. If I have distinct biological mechanisms, then I should be able to justify some sort of independence of the coding scheme.
Yeah.
That's your point.
Yeah.
And that's what we are trying to do with an estimator that relies on this assumption.
Okay. Yeah. I mean, I think I like Frank's saying about, nature's model. I mean, in a way, sort of when Ego was being developed was the sort of tail end of the very early days of MR, when there was sort of expectation that there might be sort of more larger effect variance that was, had specific biological action, including mechanistically having different effects on HDL, for example, so that you're actually testing a whole series of different mechanisms when you get that when you get coherence and when you don't get heterogeneity. But in a way, when Ego was being developed, I mean, we gave this sort of example, heritable confound with BMI and CRP, which was the same example as I used a year before in the paper, because there weren't that many examples. But I think what the sort of last 15 years or whatever, 12 more years of GWAS have shown is just that it's very unlikely that you're going to get very large numbers of independent variants where a chunk of them are not working through heritable confounding. As you start getting large numbers of variants, it's become very clear that in many situations, many of them are acting through heritable confounding. Like, many of the variants for CRP are BMI variants, and then a chunk of them are smoking variants, etc. So, and of course, heritable confounding is as you showed in the example, is one way of obviously violating inside. The sort of most obvious way of inside violation is heritable confounding. So maybe the sort of default biological model now would suggest that very often you would anticipate there to be inside violation.
I think what Matt was saying, which I still is that forget biology if gamma J, alpha J are independent, then any function of gamma J and any function of alpha J are independent. Now, question, does that mean, because I haven't grokked all the coding stuff here, does that mean that any coding, your original, you will never get if they were independent, will you get the code? Can you get the coding problem if the difference is just multiplying something by a function of gamma J, even the sign, because that's still independent of alpha J.
So this has to be the last question, a relatively short answer, because we've been signaled.
The only reason why I'm not 100% confident in responding is because when I do the coding, some function of gamma J are going to show up together with alpha. That's why I'm not 100% sure about the answer to Matt.